Welcome to a brief recap of the lab on capacitors, and what I'd also like to do is introduce another topic that will help you with the worksheet that you have for your homework. If you remember from the lab, what we did is we took a look at two parallel plates. In this case I have it disconnected from the battery. And what we did was we looked at adding charges, for example adding positive charges to the top plate, taking them from the lower plate, or reversing the sequence, something like this, playing with the charges on the plates. And then what we did was we looked at the voltage between the two plates. So we hooked up a voltmeter, something like this. And what you noticed in the lab is as you increased, for example, the charges on the plates, you would increase the electric potential V between the plates. That should basically make sense, except that we noticed that these two things were proportional. In other words, you can actually work out a constant of proportionality for two particular arrangements of plates. We called that constant of proportionality capacitance, given it the symbol C, and we said we defined it essentially as the charge on the plates divided by the voltage, electric potential V, between the two plates. And you'd see that for any Q, you get a change in voltage and they stay in a constant proportionality like this. So that's just a quick review of what we saw in the lab. What I'd like to do now is to basically take a closer look at these two quantities, the Q on the top and the voltage on the bottom, and extend our ideas in both cases to basically be able to make a fuller description of what capacitance is and what it depends on. So what I'm going to start with is talking about the charge on the plates. So now what I'm going to do is I'm going to vary the charge on the plates, but I'm not going to look at the voltage now between the plates. What I'm going to look at is the electric field between the plates. And so what I'm going to do is go ahead and turn on the electric field lines. And you'll see here, this is something you probably should expect, that the more charge you place on the plates, the greater the electric field. And if you have the simulation open, you'll have it open for the worksheet that you do. You can kind of play around with this. And so in this case right here, you can see it appears to be that there's some sort of a direct relationship between the amount of charge, Q, and the electric field, E, between the plates. Now, it's not quite as easy as that, though, because you'll notice is this. In this case right here, I've increased the amount of charge on the plate, and I definitely have a stronger field. But if I make changes to the plate, for example, if I take the plate and I spread it out and I make it something like this, you can see the field lines spread out when I spread out the plate. So it seems like a plate with greater area then is going to have less field. And so if I were to bring the electric field meter over, I could do some kind of a test where you can kind of see that this is giving you a reading on the magnitude of the electric field. If I take the size of the plates and decrease them, you can see that essentially the amount of charge on each plate Q is exactly the same. It's trapped there because there's no battery connected. There's no place for the charges to go. And the electric field will increase if I push them together. Now, one way to think about this is if you consider the plate, I'll take the charge down to quite a small value. If you consider each charge on the plate creating one of the field lines, that's one way to think about this. It makes sense that as I add more charge, I have more field lines. But the other thing that controls the strength of the field between the plates is how closely spaced those field lines are. That's another definition of our electric field. Field lines that are more widely spaced are weaker. So we have to take account both the charge and the area. And one way to do this, and this is the way we're going to do it on the worksheet that you have, is by thinking about the density of the charges that are located on the plate. It'll look a little something like this. Again, we're thinking about the charge portion of the capacitance number. And what we'd say is this. It's not the charge that seems to be, somehow charge, Q, is related to the electric field. It's somehow related to it. But we can't just say it's just the charge. It seems to be related to the charge and the area. And if we set this up to be charge per unit area, we can define this thing. We're going to give it just a symbol of sigma. And that number represents the density of the charge on the plates. In other words, it captures how many and how closely spaced they are. And it turns out it's this number that is related to and directly proportional to E. Now the constant of proportionality is a number that we haven't used before, but it's a constant that's on the equation sheet, and it's called the permittivity constant. It's a constant associated with electricity. This is not something that we have done in the lab, so this is why I'm adding this information to help you out with the essentially for the worksheet, because you'll need it. But what you can see here is if I take this into account, now notice that as the density or the charge per unit area on the plates increases, the field strength between the plates increases proportionately. And that's what we just said with that equation on the top. Okay? All right, so that's the first relationship we'd like to talk about. And then the second relationship now is what we'd like to do is talk a little bit about the voltage between the plates. I've gone back to the setup with the voltmeter attached here. And you should remember from previous instruction that electric potential V is the work per unit charge to move a charge through a uniform field, in this case, between the two plates. So in this case right here, you'll notice is that if I change the size of the plates, something like this, you can see I get a change in the electric potential between the two plates. We'll see that in a second because I'm changing this electric field. The other possibility is I can change the separation between the two plates. And you notice that because this is the work done in moving a charge between the two plates, since it's moving through a different distance between the two plates, I can also affect this. What this means is that changing the physical characteristics of the plates, changing the area or changing the distance between the plates, can also have a effect on the electric potential V between the two plates. And we need to take a look at that as well. Now in this case, what we're doing here is, again, we're taking a look at capacitance, but we're taking a look at in terms of first Q and now in terms of this electric potential V difference between the plates. And now it's best to just go back to an equation that we already have used. It's on the equation sheet. It's the equation for the field between the plates. So in other words, if I have a certain field E here between the plates, we derived this before. That's equal in magnitude to the voltage between the plates divided by the distance between the two plates. Okay, so just to summarize what we've done here is we've taken a look at the two aspects of capacitance. First of all, the charge. Second of all, the electric potential difference V between the two plates. And we've noticed that there are other factors that affect both of those numbers. In the first case with Q, that's affected by the charge density. And what that does is it brings in area as one of the variables that's going to affect capacitance. Looking at the bottom equation, if you look at the voltage by changing the distance between the plates, I can have an effect on one of the terms associated with the capacitance. And you'll see that both of these side terms, the charge density on the top and the electric field on the bottom, are also tied together with the idea of electric field. So basically what the worksheet that you're going to work on is going to tie these together so that we can extend our definition of capacitance to include the physical features of the capacitor, which include the area of the plates and the distance between the two plates. And you're going to derive this equation and kind of play around with changes on the two plates on the new worksheet. All right, so hopefully that helps you out as far as the worksheet's concerned. I will also post a solution for it to help you out. You can expect also a reading from the textbook on the topic of capacitance, and that'll be your topic for this week where we don't have class. Thanks a lot for joining me. and have a great Easter break. Take care.